So welcome everyone. We're continuing our course in algebraic topology. I'm Norman Wahlberger. We're here at the University of New South Wales. Today I'd like to informally introduce some basic ideas from abstract algebra. So some of you have had some abstract algebra before, but some of you may not have. So I want to sort of lay out a broad landscape of different algebraic objects that we sometimes need to use in algebraic topology. So there's a fair number of different notions around. So some prominent ideas or prominent abstract objects are fields, notion of a field, notion of a ring, notion of a vector space, a group, and there are also these things called hypergroups, which maybe we'll mention, which are not usually so well studied. Field, ring, vector space, group, hypergroups, and there are more, but this is probably a pretty good starting list. So basically what we have here, there's some general patterns that happen over and over again. We have basic ingredients are some kind of specified object or expression. And then we have some notions of operations with those objects or expressions. Some operations, typically like addition and multiplication. Some operations and various laws that they satisfy. There might also be some special elements that play distinguished roles in that particular topic. Okay, and the basic idea of abstract algebra is to generalize from some situations that are pretty familiar to us to cover more wide-ranging situations. So what we want to do is we want to have a look at some examples. And all of these kinds of objects are best understood in the context of examples. Okay? Usually there's about 3 or 4 different fundamental examples for each one of them, and once you've understood them, you're well on your way to understanding the general theory, although there's more to be done. Okay, so what kinds of objects and operations are we talking about? Let's go right back to so a very kind of beginning thing. The most fundamental, simplest algebraic system are the natural numbers, or counting numbers, and the operations that everybody is familiar with are addition and multiplication. And we're not going to define those or anything, but let's just list a few properties of addition and multiplication that are important. They have special names. So one of the properties is the commutative law, so that a plus b is equal to b plus a. That's the commutative law for addition. There's also a commutative law for multiplication. So these are the commutative laws. Then there are some associative laws, so that if you combine a plus b and then c, that's the same as a plus b plus c. And same thing with multiplication. So these are associative laws. Then there's the distributive laws, which are that a times b plus c equals a times b plus a times c. And the convention also is that the multiplication takes precedence over the addition. So this really means a times b plus a times c. And there's another one in the opposite order if we like. If we have a plus b times c, we could write that as a times c plus b times c. So distributive laws. And then we need to mention one special element. The natural numbers has a very special element, namely the first one. And this special element, 1, has the property that 1 times anything, 1 times A, is always A. And this is the property of what we call an identity element. So this is a multiplicative identity. Now there are some other properties of the natural numbers. Okay, these are not the only ones, but these are good starting points that all school kids learn. So you might ask, well, what do we call a framework like this where we have 2 operations satisfying these laws? And the embarrassing answer is I'm not really quite sure. I'm not sure how one officially generalizes this. In fact, generally people don't consider generalizing this framework too much. No doubt somebody has, but it's not very prominent kind of thing. But it's good to mention first. And when we go up one step to the integers, then we get something that is very commonly generalized. So with the integers, we include not just the natural numbers, but prominently also 0 and the negative numbers. Okay, so the same laws hold. Oh, question?
Just checking you're not considering 0 to be a natural.
Yes, in my framework, 0 is not a natural number at this point.
Oh.
Because historically, 0 actually only entered the story relatively late in the piece. Although that's a convention. But with the integers, we definitely have 0. We have negative numbers. In particular, we have this number -1. So the presence of this -1 is that it's the additive inverse of 1. So the special new features here are that 0 plus anything is the anything. So 0 is an additive identity. So in the integers, there's the multiplicative identity 1, but also now an additive identity 0. And then this number -1 plays a special role because -1 plus 1 equals 0. And that's really the origin of a new operation called subtraction. So we can define A minus B to be A plus -1 times B. So we can build up subtraction from addition and multiplication together with this new element -1. Okay, so we get a new operation. So now we have 3 operations: addition, multiplication, and subtraction. And these are sort of inverse operations. Or another way of saying that is that every element A has an additive inverse so that's called minus A, which is actually -1 times A, such that A plus minus A equals 0. So these are the integers. And this is a basic example of what we will be calling a ring. All right. So the integers are the fundamental and most fundamental basic example of a ring. Okay, but that's not quite arithmetic as we know it, because we have 3 operations, but we want 4 operations. We want to divide as well. So when we want to extend our arithmetic, as we do in grade 6 or something, to include division, then we have to move up to a bigger arena, to the rational numbers. And this is a field, so a rational number field. And so it's probably useful to be rather clear about the rational numbers, because they're really the fundamental building block for arithmetic. So now we're going to have 4 operations, addition and subtraction, which are inverse operations, and addition, and then this new operation, division, and these are also inverse operations. Okay, so what is a rational number? Well, so the definition of a rational number, one can think of it many ways, but we're going to just think of it as an expression of the form a over b, where a and b are integers, and b is not equal to 0, together with the particular notion of equality. And the notion of equality is that a over b equals c over d, precisely when AD minus BC equals 0. So for example, 2/3 is the same as 4/6, which is the same as minus 20 over minus 30, etc. Let me say just a few words about notation, and I have to say a little bit about set theory. So as you may know, I'm not a big fan of infinite sets. I think that modern mathematics is askew in its reliance on infinite sets to set up foundations of mathematics. So I prefer not to think in terms of infinite sets, but rather in terms of types of mathematical objects, more in the line of what a computer scientist would do. Okay? So the computer scientist, when he talks about rational numbers, not that he's got a big basket of all the rational numbers and he's pulling them out. He's more rather is talking in terms of what you have to write down on the page to specify the type of a rational number. So that's what we're doing here. So when I use something like Q, I don't really mean the set of all natural numbers. For me, that means the type of a mathematical object, the type of rational numbers. And this notation here with this epsilon with a little line sticking out of it is my way of saying that these objects have the type of integer. Okay, you could say this in Haskell or some computing language in another way. We're not going to make a big deal out of that, but I just want to emphasize that we're not using infinite sets, because, of course, infinite sets don't exist. All right, so we have the definition of rational numbers, and now what about the operations? Well, I guess the operations are familiar enough. We have addition, subtraction, multiplication, and division for rational numbers. And what sort of key new properties do we require to make this a field? Well, the main new property really is that every non-zero rational has a multiplicative inverse. So for example, if we take 2/3, its inverse is 3/2. And the crucial property that we want a multiplicative inverse to have is that when we multiply A times A inverse, or A inverse times A, that we should get 1, the multiplicative identity. And it's important to say that every non-zero rational has this property. There is no number. This does not exist. There's no number so that when you multiply it with 0, you get 1. So 0 inverse does, of course, not exist. Okay, so that's sort of the main new property that we add to a ring to make a field. For beginning students of abstract algebra, the field is probably the most natural thing to think about first because it's closest to our intuition. The structure of a field is a little bit more rigid than the structure of a ring. In fact, it's a lot more rigid than the structure of a ring. So a general field looks more like the rational numbers than a general ring looks like the integers. A ring is a somewhat more extensive or maybe flabby concept, and a field is more tightly constrained by requiring this multiplicative inverse. Okay, so now we want to talk about other examples. What are some other examples of rings? What are some other examples of fields? All right, so other examples of a ring. Well, of course, we started off with the integers. So the crucial thing is that we want to have an addition, we want to have multiplication, and we want the various commutative, associative, and distributive laws to hold. But sometimes we're a little bit flexible. The commutative law may or may not hold. Okay? So in general, we allow also non-commutative rings in the following sense. So that A times B does not necessarily have to equal B times A. So this is allowed. But as far as addition goes, this is required. So I'm going to give two very important examples of rings. One which is commutative, like the integers. One which is not commutative and goes beyond that framework. So an example, a very important example of a commutative ring are rings of polynomials. Okay, so ring of polynomials. And we can do this well over Z. So we could think of, no, maybe I'll use alpha. We can think of a ring of polynomials Z alpha, which contains things like 3 minus alpha plus alpha squared plus alpha to the fourth, for example. There's a polynomial. And we can add and multiply polynomials in the usual way. And they satisfy the commutative, associative, and distributive laws. Or we could also think about polynomials with rational number coefficients, say Q alpha, something like 2/3 plus 4/9 alpha squared minus 1/100 alpha to the fifth. All right, that would be a polynomial with rational coefficients. And if you add two of those, or you multiply two of those, then also you get another one of the same type. In terms of a non-commutative ring, the main example is the ring of matrices. Okay, so the ring of matrices. And again, we have some choice what kind of coefficients we want to allow. For example, let's look at 2 by 2 matrices. Let's say M2 with integer coefficients. Okay, so I'm talking about things something like 2, 3, minus 1, 4. And let me remind you how you multiply these two things. Okay, if we want to multiply two matrices like this, the way we do it is 2 times 1 plus 5 times 3 is 17. 2 times 6 plus 3 times minus 1 is 12, minus 3, that's 9. Minus 1 plus 20 is 19, and minus 6 minus 4 will be minus 10. That's how we multiply matrices, and adding them, of course, is just point-wise. So 2, 3, minus 1, 4, plus 1, 6, 5, minus 1 is 3, 9, 4, 3. So this ring has many of the features of the integers, but not all of them. So there's a special matrix which acts like 1. So the number 1 sort of corresponds to this particular matrix. The number 0 in the integers corresponds to this matrix. The number minus 1 corresponds to this matrix. But this is not a field. It's not a field because the elements do not have multiplicative inverses always. Okay? So this is not a field because a general 2 by 2 matrix doesn't necessarily have a multiplicative inverse. Since multiplicative inverses don't exist. Don't always exist. Sometimes they do. And I remind you from linear algebra that a matrix has an inverse precisely when its determinant is non-zero. So precisely when the determinant of the matrix M is a non-zero. That's the condition on having a multiplicative inverse. So that's an example of a non-commutative ring. Example of commutative ring, the integers, polynomials, non-commutative ring, ring of matrices. All right, what about examples of fields? And of course, we're just touching the surface of these subjects. There are many more examples of rings, of course, but just in terms of an introduction, there's probably a good orientation. Those are good examples to keep in mind. Okay, so examples of fields, or other examples of fields. Well, if I ask the average student what's an example of another field, they'll immediately say, well, the real numbers. Yes. And then if I ask them, well, what exactly are the real numbers? Then there's a lot of humming and hawing that goes on, and well, it's somewhere in some book there's some explanation. So the real numbers is highly problematic if you want to actually do things correctly. So it's probably not such a good example for a field. Similarly, the usual complex numbers. Okay. But there are lots of nice fields that we can still talk about. For example, we can talk about the complex rational numbers. Okay, things of the form a plus bi, where a and b are rationals. And the addition is in the usual way. So if we added those two things, we would get 7. 3 minus 3 halves would be plus 3 halves I. But the product is, I'll do a simpler one so it's easier. The product is obtained by using the rule that I squared equals minus 1. So this is 2 plus 3, I guess that's 5. How many i's do we have? 3i minus 2i, so plus I. And why is it a field? It's a field because of the following reason. If we want to invert 2 plus 3i, if we want to find a multiplicative inverse, that's the crucial quantity to have a field, that every non-zero element have an inverse, then how do we find the inverse? Well, we multiply top and bottom by 2 minus 3i, giving us 2 minus 3i, and on the bottom we get 2 squared plus 3 squared. So that would be 4 plus 9 is 13, so 2 over 13 minus 3 over 13i. And you can see that this works for all a plus bi as long as a squared plus b squared does not equal 0. In other words, every non-zero complex rational has a multiplicative inverse. Okay, another example of other kinds of fields are the finite fields. And I'm only going to tell you about finite prime fields because the non-prime fields are a little bit more complicated to describe. So this is a non-standard description of a finite prime field that I'm going to give you now. So I'm going to define a Q. Okay, I'm not really sure what would be a good terminology for it. I want to put a P somewhere. So if I put a P here, it probably is not such good notation, but I might do that anyway. Okay, so let's just put Q sub P. And what is this? Well, it's things of the form a plus b, where a and b are integers, with the following notion of equality. With a new notion of equality. The new notion of equality is that a over b equals c over d, precisely when AD minus BC is divisible by P, and P is a prime. Like 3 or 5 or 7 or 11, etc. 2 works too. And what are the operations on this perhaps rather strange new kind of object? Well, the operations are exactly the same as they are for the rationals. Now, those of you who have studied finite fields may be used to thinking in terms of modular arithmetic. This is another variant. This is another way of thinking about the finite fields, which makes it much more analogous to rational numbers. So, for example, how do we do some operations? Let's say we're working p equals 7. All right, let's do some arithmetic. Mod in this field Q7. So what is 2/3? Oh, I should have also, I forgot to say one thing. There's a condition on A and B. Right? For the rationals, the denominator cannot be 0. For these P sort of rationals, we require a different condition. I better put it up here. So B is not divisible by P. That's the condition on the denominator that replaces the usual condition of being non-zero. All right, so let's add 2/3 plus 4/5. Are these valid numbers? Yes, they are, because the denominators are not divisible by 7. How do we add them? Well, we add them by just the usual thing. It's 10 plus 12. 10 plus 12 is 22 over 15. Can I simplify that? Well, yes, I can, because this is going to be the same as 1 over 15. Can you see that? I'm allowed to subtract 21 from here because 21 is a multiple of 7. So why are these two things equal? Well, because the difference between this and this and this and this is divisible by 7. In fact, I can get rid of the 15. I can replace that with 1 over 1. So this is actually the number 1. So it's a pleasant exercise then to show that it's a pleasant exercise to show that every element in, say, what we're calling Q7 is one of the following list. 0 over 1, 1 over 1, 2 over 1, 3 over 1, 4 over 1, 5 over 1, 6 over 1. Which we can, if we want to, think of it rather just as the numbers 0, 1, 2, 3, 4, 5, and 6. And this way we recover modular arithmetic. We get modular arithmetic. But for many purposes, if you're doing a lot of calculation, it's actually sometimes easier to work in the context of rational numbers rather than integers, because dividing is a lot simpler with the setup of rational numbers. So in the standard literature, this field is usually called F7. So what I'm calling Q7 is often called F7. And another way of thinking about it, and another thing that it's called, is Z mod 7Z. So these things are all pretty well the same. And where do we need the property of primeness? We need the property of primeness again for the crucial property of the field, that every non-zero element has a multiplicative inverse. If we replace 7 with 6, then we would still get a ring, but we would no longer get a field. So as another exercise you might like to think about, if you do the same for so 6 instead of 7, then Q6 becomes, which is essentially the same as 0, 1, 2, 3, 4, 5 with arithmetic mod 6, is a ring but not a field. And one of the easier ways of seeing that it's not a field is because it has 0 divisors. This ring has 0 divisors. What does that mean? It means we can find numbers like 2 and 3. Both of them are non-zero, but when we multiply them, we get 6. But 6 is the same as 0 in Q6. Why is 6 the same as 0? Because the difference is a multiple of 6. So here we have two non-zero numbers whose product is 0. Rings that have this property are sometimes a little bit problematic, or maybe it's better to say that rings that don't have 0 divisors are a little bit more pleasant. They're like more like the integers. All right, what is another example, an important example of a field is the field that you get when you want to extend the rational numbers, say, to include a square root of 2. So this is sometimes written like this. Q adjoined square root of 2, consisting of things of the form a plus b root 2, where the product is just defined by thinking of root 2 not as a real number, but just as a symbol whose square is equal to 2. So, for example, let's say 2 plus 5 root 2 times 3 minus root 2. The way we would calculate that, just really the same kind of thing as we did with I. Just use the fact that whenever you have root 2 times root 2, you get 2. So 2 times 3 is 6 minus 5 times root 2 times root 2. In other words, 5 times 2, which is 10. So 6 minus 10 would be minus 4. And then the number of root 2's that are left over are 15 root 2 minus 2 root 2, I guess 13 root 2. So much as we did for complex numbers, you can check that this is a field. All right, so that's a very quick introduction to rings and fields. Probably in algebraic topology, we're more interested in groups. Okay? But before we get to groups, I want to mention another important type of algebraic object, which is a vector space. V over a field F. Okay? And again, if you've taken a linear algebra course, you will have seen this notion. And I'm not going to state all of the conditions. Okay? But the crucial thing is that we have sort of two operations. We have elements or objects called vectors. Say typically we might denote them with V with a little arrow telling us that these things are vectors, whatever they are. And sort of two operations. We have an operation of addition. So we are allowed to define V plus W. And we're also allowed to multiply a vector by a scalar. So it's a kind of multiplication, but it's not a multiplication of vectors with vectors. It's a multiplication of vectors with numbers from the field. Okay, so there's also a scalar multiplication. So, for example, we're allowed to talk about 3 times V, or minus 5 halves V, if our scalar field happened to be the rational numbers. But we could use any field. Once you have a field, you can talk about vector space over that field. And this object, we can visualize, a good example for it to be concrete is the field F squared. F squared consisting of vectors which have the form A, B, ordered pairs of elements from the field, whatever the field is. And if the field is the rational numbers, for example, we can visualize such a pair in the usual way by thinking of a directed line segment. There would be the vector V equals AB. We can visualize it as a vector in the plane. So a vector space is a natural algebraic object that allows us to deal with space, two-dimensional situations or three-dimensional situations. And it's a kind of very fundamental building block for other kinds of algebraic objects. I might just mention a few other vector spaces. So other vector spaces. And to be specific, let me use the rational numbers as our field. Okay? So if we're sticking with the rational numbers as our field, then some other examples of vector spaces over the rational numbers include things like, well, polynomials. Polynomial spaces. For example, we might think about, say, P sub n consisting of polynomials of degree less than or equal to n. Okay, so P2, for example, would have polynomials like 1, alpha, alpha squared, and any linear combinations. And as a vector space, that turns out to be sort of the same as the three-dimensional space F3 consisting of vectors, say A1, A2, A3. So polynomial spaces are examples of vector spaces. We said earlier that polynomials were a ring, which is true enough, but if we chop off at degree n, then we exclude the possibility of having a consistent multiplication. Multiplication goes out the window because if you multiply two polynomials, the degree goes up. So if you chop off at degree n, you can no longer multiply such things, but you can still add them, and you can still multiply any one of them by a scalar. So that becomes a vector space over the field rather than a ring. Another example would be of a vector space would be, say, matrices. So for example, we can consider maybe the 2 by 3 matrices over the field Q, consisting of matrices of the size 2 by 3. So A, B, C, D, E, F. So the 2 by 3 matrices are not a ring anymore. We can add 2 of them and we get another such thing. But for example, there's no identity element. And if we can't multiply 2 of them. So it's not as rich as being a ring, but it's still quite structured because it's a vector space. We can add 2 of them and we can multiply by scalars. So we can form linear combinations. That's sort of the crucial thing of matrices, just as we can form linear combinations of vectors or linear combinations of polynomials. All right, so rather informally, I've introduced 3 pretty important fundamental types of mathematical objects. So we've talked about rings, fields, and vector spaces, and given you a few examples of those. So next time we're going to talk about groups, but before we go on to groups, I should mention that when you develop the theory of these things in more depth, there are certain things that you do that repeat themselves almost no matter what algebraic type of object you're working with. Okay? So there are some common themes that reoccur over and over in algebra, and it's probably good to point out what those are. So if you're faced with a new algebraic object, chances are you should ask questions along the lines of the ones I'm about to list. So what are some common themes? Well, one is to define sub-objects. I better put that in quotes. Okay. So if you have a ring, you can ask, well, what are the sub-rings of that ring? That is, inside the ring, there might be some smaller rings that are themselves closed under the operations and satisfy the rules for being a ring. Or if you have a field, inside it there might be a subfield. Or if you have a vector space, inside it there might be some smaller subspaces. So that's a very important question, and a very important thing to do is to define what you mean by the sub-objects of whatever algebraic object you're dealing with. Another very important thing that one has to do is one needs to define homomorphisms. So a homomorphism is a way of relating two objects of the same category, of the same kind. All right, so if you have two rings, ring R1 and R2, then you might be interested in a map or a function which takes elements from the first ring and gives you elements of the second ring. But it's important that these functions that you're considering respect the properties of whatever algebraic object you've got. So if you have addition and multiplication, you want these to satisfy respecting addition and multiplication. So for example, you might probably want to satisfy 5a plus b is 5a plus 5b. And if you have a multiplication, you would want 5ab to be 5a times 5b. And if you have a zero element in one, you want the zero element in one to go to the zero element of the other. And if you happen to have a multiplicative identity, you want the multiplicative identity, to go to the multiplicative identity of the other one. So these kinds of relations define very important functions called homomorphisms. And then there is one more type of thing that's usually a little bit more complicated, but sort of fits in with these three. We need to define quotient objects. Okay, what happens when you divide out by dividing one ring by another, or dividing one field by another, dividing one group by another, dividing one vector space by another? So if you set that up right, then you have new ways of getting objects by doing these sub-constructions or quotient constructions. All right, this is a little bit vague now, but in the next lecture, we're going to address the algebraic objects that we're mostly interested in algebraic topology, which are the groups. Okay, so we're going to talk about group theory. And in group theory, there's a big division between commutative groups and non-commutative groups. That's the big separation. Commutative versus non-commutative. And both of them are important for algebraic topology. So we're going to revisit these ideas, sub-objects, homomorphisms, quotient objects, in the context of group theory, which is where we're mostly interested in things. Okay? There's no point in me spending weeks doing it for rings and fields, because that's of somewhat marginal interest for us. But for groups, these are very important notions. Okay? So next time we're going to introduce groups, commutative groups, non-commutative groups, homomorphisms between them. And we'll look at some interesting, important examples. So I'll see you then.